In this lecture, we discuss about beta function. The beta function, also known as the Euler's integral of the first kind, was introduced by Leonhard Euler in 18th century. It served as an important tool in mathematical analysis, particularly in the study of special functions. The functions emerged as a part of Euler's work on integrals involving product of powers and exponential functions, and it later gained importance due to its connection with the gamma function, explored in depth by Andrine Marie Legendre and others. The beta function plays a central role in various areas of mathematics and physics, particularly in calculus, probability, and statistics. It is also an essential building block in the study of hypergeometric functions and other advanced topics. Beta function is denoted by beta of mn and is given by beta of mn is equal to integration of x to the power m minus 1 into 1 minus x whole to the power n minus 1 under the limit 0 to 1 with respect to x, where m and n are any positive numbers. Properties of beta function. The first property is beta of mn is equal to beta of nm. So this is called symmetric property of beta function. So let us try to prove it. We know that beta of mn is equal to integration of x to the power m minus 1 in bracket 1 minus x whole to the power n minus 1 under the limit 0 to 1 with respect to x, where m and n are positive numbers. Let us so let us replace. We know that we have the property of integration, definite integration of f of x under the limit 0 to a, which can be written as integration of f of a minus x under the limit 0 to a with respect to x. So now here upper limit is 1, so x can be written as 1 minus x to the power m minus 1, and this 1 x is replaced by 1 minus x to the power n minus 1 with respect to x, which can be written as integration under the limit 0 to 1 of 1 minus x to the power m minus 1. This plus 1 and minus 1 will cancel, and we have x to the power n minus 1 with respect to x. So it can be written as integration of 1 minus x to the power m minus 1 into x to the power n minus 1 dx under the limit 0 to 1. And this is nothing but, we can also write down integration of x to the power n minus 1 1 minus x whole to the power m minus 1 under the limit 0 to 1 with respect to x. And now if we compare this with the definition of beta function, so in place of m it is n, and in place of n it is m. So we can write down beta of nm. So hence beta of mn is equal to beta of nm. So here no need to confuse over there that we have to write down m first or n first. We can write down m and n, or we can interchange m and n anywhere. So this is the very basic property of beta function. Let us take the second property of beta function. Integration under the limit 0 to 1 of x to the power m 1 minus x whole to the power n with respect to x, which is equal to beta of m plus n and m plus 1 and n plus 1. We know that beta of mn is equal to integration of x to the power m minus 1 in bracket 1 minus x whole to the power n minus 1 under the limit 0 to 1 with respect to x, where m and n are any positive numbers. Now Consider x to the power left hand side. Let us take the left hand side. X integration under the limit 0 to 1 of x to the power m into 1 minus x whole to the power n dx. Now, this can be written as we are adding and subtracting plus and minus 1 in the same thing in the second part. So this is what it is: integration of x to the power m plus 1 minus 1 into in bracket 1 minus x to the power n plus 1 minus 1 with respect to x under the limit 0 to 1. So now if we compare this with this formula, so in place of m it is m plus 1, in place of n it is n plus 1. So this can be written as beta of this can be written as beta of m plus 1 and n plus 1, beta of m plus 1 into n plus 1. Hence, integration of x to the power m into 1 minus x whole to the power n under the limit 0 to 1 with respect to x, which is equal to beta of m plus n and n plus 1. Let us go to the property number 3. Beta of mn is equal to 2 times of integration of sine to the power 2m minus 1 t into cos to the power 2n minus 1 t under the limit 0 to pi by 2 with respect to t. So we know that what is beta of mn? Beta of mn is equal to integration of x to the power m minus 1 whole 1 minus x to the power n minus 1 under the limit 0 to 1, where m, n are any positive numbers. Let us give it equation number 1. Now, let us put x equal to sine square t. Then dx is equal to derivative of sine square is 2 sine t, again derivative of sine t is cos t dt. So if x equal to sine square t, then dx is equal to 2 sine t cos t dt. Also, if x tending to 0, let us change the limit. If x tending to 0, sine 0, if x tending to 0, then it is what? Sine square t equal to 0, which is equal to sine 0. So it gives us t equal to 0. And if x tending to 1, then it will become sine square t is equal to 1, which can be written as sine pi by 2. So t, when x tending to 1, then t tending to pi by 2. Hence 1 becomes beta of mn is equal to, limit should be 0 to pi by 2, integration under the limit 0 to pi by 2. X is sine square t whole to the power m minus 1. 1 minus x is equal to sine square t whole to the power n minus 2, and dx is equal to 2 sine t cos t dt. Now, which can be written as this 2 we have taken outside, this 2, integration under the limit 0 to pi by 2, sine to the power 2m minus 2, and this power, its power has 1, so 2m minus 2 plus 1 t. Similarly, this 1 minus sine square t is nothing but cos square t. So its power is cos square 2n minus 2, and this its power is again 1. So this is 2n minus 2 plus 1 uh, of t. Now 2m minus 2 plus 1 is 2m minus 1, and 2n minus 2 plus 1 is 2n minus 1. So it can be written as 2 times of integration under the limit 0 to pi by 2 of sine to the power 2m minus 1t into cos to the power 2n minus 1t, and dt is also there. Dt is missed over here. So dt is always over there. Therefore, beta of mn is equal to integration of 2 times of integration of sine to the power 2m minus 1t into cos to the power 2n minus 1t under the limit 0 to pi by 2 with respect to t. Property number 4, integration under the limit 0 to pi by 2 of sine to the power pt into cos to the power qt dt, which is equal to 1 upon 2 beta of p plus 1 by 2 and q plus 1 by 2. Let us try to prove it. So we know that beta of mn is equal to 2 times of integration under the limit 0 to pi by 2 sine to the power 2m minus 1t cos to the power 2n minus 1t dt. We have just proved this result in the last property number 3. Now here, if we put 2m minus 1 equal to p and 2n minus 1 is equal to, so what will happen? What is the 2m equal to 1 plus p? So m is equal to p plus 1 by 2. Similarly, 2n minus 1 equal to q, then 2n is equal to q plus 1 and n equal to q plus 1 by 2. Then 1 will become beta of p plus 1 by 2 q plus 1 by 2, which is equal to 2 times of integration under the limit 0 to pi by 2 sine to the power pt into cos to the power qt with respect to t. So therefore, what is the 2 times of integration of sine to the power pt cos to the power qt under the limit 0 to pi by 2 with respect to t, which is equal to beta of p plus 1 by 2 q plus 1 by 2. So let us replace this 1 by 2 over here. Then we have the desired result. Therefore, integration of sine to the power pt cos to the power qt under the limit 0 to pi by 2 with respect to t, which is equal to 1 upon 2 beta of p plus 1 by 2 q plus 1 by 2. So this is what this result shows that the generalization of the reduction formula we have already seen in the reduction formula. If the multiplication of sine to the power nt and cos to the power mt dt under the limit 0 to pi by 2, where m and n both should be positive integers. But if it is not integer, then we cannot apply that formula. We can apply this formula. So this formula is true for all values, all positive values of p and q. So this beta function is the extension of the reduction formula for sine to the power mx integration of 0 to pi by 2 sine to the power mx into cos to the power nx dx. Property number 5 is beta of mn is equal to integration of x to the power m minus 1 upon 1 plus x to the power m plus n under the limit 0 to infinity dx. That can be also written as integration of x to the power n minus 1 upon 1 plus x to the power m plus n under the limit 0 to infinity with respect to x. So let us try to prove this result also. We know that beta of mn is equal to integration of x to the power m minus 1 into in whole bracket 1 minus x to the power n minus 1 under the limit 0 to 1. Now let us put x is equal to t upon 1 plus t. Then what is the value of dx? Dx is equal to, this is what we have to apply the division formula. So numerator, denominator, 1 plus t is denominator. Derivative of numerator t is equal to 1 minus denominator, numerator is t, and this is multiplication, and derivative of denominator 1, derivative of 1 is 0 and derivative of t is 1. This is 1 and whole divided by 1 plus t whole square. So this can be written as 1 plus t minus t. So this will cancel 1 upon 1 plus t whole square dt. So dx is equal to dt upon 1 plus t square. Okay, what will happen if we change the limit? Also, if x is equal to t upon 1 plus t, so x time of 1 plus t is equal to t, which can be written as x plus tx is equal to t, or t minus, let us replace this to this side, t minus tx, which is equal to x. So if we take t outside, then t times of 1 minus x is equal to x, and t is equal to x upon 1 minus x. Now, if we put x is equal to 0, x equal to 0, what will happen? This is 0 upon 1, 0 upon 1, which gives us 0. And similarly, if we put x is equal to 1, x is equal to 1, so something upon 1 minus 1 means 0, something upon 0 is infinity. So if x tending to 0, t tending to 0, and if x tending to 1, then t tending to infinity. Then 1 becomes beta of mn is equal to, it is 0 to infinity, integration under the limit 0 to infinity. X, what is the value of x? X is nothing but, uh, this is the value of x, t upon 1 plus t whole to the power m minus 1, 1 minus t upon 1 plus t whole to the power, this whole to the power n minus 1 into dt upon 1 plus t whole square. If we simplify it, beta of mn is equal to integration under the limit t upon 1 plus t to the power m minus 1, 1 minus t upon 1 plus t to the power n minus 1, dt upon 1 plus t whole square. Now, if we simplify this one, this is 1 plus t minus t, so this minus t plus t will cancel. Its power is 1 upon 1 plus t whole to the power n minus 1, t upon 1 plus t whole to the power m minus 1, dt upon 1 plus t whole square. So just look here, it is 1 plus t to the power m minus 1, 1 plus t to the power n minus 1, 1 plus t whole to the power 2. So we can write down t to the power, its power is m minus 1, 1 to the power n minus 1. So we have only t to the power m minus 1. And in the denominator, 1 plus t to the power m minus 1, n minus 1 plus 2. So this minus 1 is minus 2 and plus 2 will cancel. So we have beta of mn is equal to integration of t to the power m minus 1 upon 1 plus t to the power m plus n dt under the limit 0 to infinity. So therefore beta of mn is equal to integration of x to the power m minus 1 upon 1 plus x to the power m plus n under the limit 0 to infinity with respect to t. But we know that, again, we know that beta of mn is equal to beta of nm. So this m can be replaced by n. So now we are able to write down this as beta of mn equal to integration of x to the power n minus 1 upon 1 plus x to the power m plus n under the limit 0 to infinity with respect to t, which is equal to integration of x to the power n minus 1 upon 1 plus x to the power m plus n under the limit 0 to infinity with respect to t. So this is true for m and n both. Let us see the property number 6, relation between beta and gamma function. So beta of mn is equal to gamma of m, gamma n divided by gamma m plus n. So this is very important formula, and this is the relation in which we are able to find out the relation between the beta and gamma function. Property number 7, uh, we have already seen this one, and it can be written as, if we apply this beta relation of between beta and gamma function, so 1 upon integration of sine to the power pt cos to the power qt under the limit 0 to pi by 2 with respect to t, which is equal to 1 upon 2 beta of p plus 1 by 2 q plus 1 by 2. So if we apply this above formula, we can write down 1 upon 2 into gamma p plus 1 by 2 into gamma q plus 1 by 2 whole divided by p plus q plus 2 upon 2. The property number 8 is called duplication formula, and it is given by gamma of m into gamma m plus 1 by 2, which is equal to root pi upon 2 to the power 2m minus 1 into gamma 2m. So these are some basic properties of beta functions. Let us take some applications of beta functions. So the first application is on in probability and statistics. The beta function is used to define the beta distribution, a widely used probability distribution in Bayesian statistics and machine learning. Its second use in evaluation of integrals. The beta function simplifies the evaluation of certain complex integrals involving powers and binomials. The third application is gamma function relationship. It provides a bridge between the gamma function and factorials, essential for combinatorials calculations. And then combinatorics. Beta function appears in formulas involving binomial coefficients and partitions. It is also useful in physics, in which it is used in solving problems in quantum mechanics, statistical mechanics, and thermodynamics. The sixth use of beta function is in engineering. It plays a role in signal processing in electronics engineering, where integral involving powers of sine and cosine arise. It also used in the number theory. It appears in evaluation of zeta functions and other series related to prime numbers. Beta function is also used in hypergeometric functions. The beta function forms part of the definition and analysis of hypergeometric functions. In fluid dynamics, it is used in the study of boundary layers and viscous flows where exponential decay is modeled. In computational biology, it appears in modeling population genetics and other probabilistic systems in biology. So these are some basic applications of beta functions. Thank you.